All right, so welcome everybody to today's PRIISM seminar. We're delighted to be joined by Professor Daphna Harel, our own Daphna Harel. And so Daphna is an applied statistician who studies issues of measurement and modeling in the applied health sciences. Her research focuses on modeling challenges for data arising from self-reported questionnaires and crowdsourcing and requiring the use of multi-level models. Daphna received her PhD from the Department of Mathematics and Statistics at McGill University. And with that, I'll turn it over to you, Daphna. Thanks.
Thank you so much for that introduction. Here, let me pull up my slides. Okay, I will assume with that you can all see my slides and hear me. So today I want to talk to you about a project or a set of projects really that I've been working on for, I don't know, the large part of 6 years. And I'm going to do this through a case study of the Patient Health Questionnaire 9. So patient-reported outcomes are surveys that assess aspects of patient lives that are super important to them. You know, often with data, we are used to thinking like, oh, did this patient get better or not? Did they pass away or not? But when you have a chronic illness, things like your functional abilities, things like your chronic fatigue, your depression, those are of interest to understand so that we can better help people live, happy and productive lives. So how do we do this? We often will ask people this like multi-item questionnaire. So we'll ask them like 20 questions based on, do you feel sad? Do you feel depressed? Do you cry a lot? And then we'll assume there's something that's underlying your responses to these questions. Now, when I started my PhD, I worked with a set of rheumatologists up in Montreal, and they would literally hand their patients a 40-page booklet of questionnaires that they wanted the participants or patients to respond to. And you have to imagine, first of all, who wants to fill out 40 pages of a questionnaire? But also, like, even if you do, isn't the data you get by the end of it probably not the best, because like just burden and fatigue and issues like that. So patients may be asked to respond to many different scales, especially in research studies, but even like in clinical practice, when you go to your doctor's office, maybe a few of these are applied. So to alleviate this burden, researchers will try to shorten patient-reported outcome measures. But I think that this methodology to do so is often underdeveloped. So what people will do is generally one of three things. Either they'll get a qualitative expert assessment of item content. So they'll get a bunch of experts in a room and say, here's the full-length scale. If I could only pick out a few items, which ones would you pick out? They might fit a statistical model, like a factor analysis or item response theory model, which I'll go through soon. So if you're not familiar with those, no worries. And then look at a certain parameter estimate called a factor loading and say, well, these just don't seem to be doing a good job at, at being questions to measure the thing we're trying to look at. So I'm just going to stop asking them. Or my favorite is literally no justification. People just say, here's a new shortened form. I love it. You should use it. So these are good ideas or maybe less good ideas. Some of them are good ideas. But what's really important here is that any of these methods leave the final selection of items to the researcher's prerogative and not through objective and reproducible criteria. So get a different set of experts in a room, you might get a different expert assessment of which items are important. And because of this, often for a single long-formed scale, multiple shortened forms will exist. So I'm going to talk to you about the Patient Health Questionnaire 9, or the PHQ-9. Now it's a 9-item outcome measure that measures levels of depressive symptomatology in the last 2 weeks. You may be familiar with it. It's one of the most commonly used depression measures. I know I've seen it used at my own doctor's offices. So it's 9 questions, each rated on 0 to 3 and some sort of Likert scale for a total score ranging between 0 and 27. So if you get a high score on this, you say like, yes, I have a lot of these symptoms, then you might get referred to a psychiatrist or a clinical expert, some sort of doctor, who will say, yes, you satisfy the criteria for major depressive disorder or any other depressive disorder. So what people will do with these scales is find some sort of cut point and say, well, if you score more than a 10, this is a high likelihood of having major depressive disorder. And if you score less than a 10, well, you're probably fine, or you're within kind of normal ranges. And the PHQ does a good job at this. It has a sensitivity and specificity around 0.78 and 0.87, respectively, shown on like very large data sets. So we're pretty, happy with those estimates. And it's often used as a screener for these like semi-structured, fully structured interviews, or even just by itself, because it provides participants direct perspectives. Your feelings are things you can report about more than some doctor can say, oh, check mark, check mark, check mark. This is how my diagnosis for you. So 9 questions. I said this talk is about shortening questionnaires. You might say, well, is it worth shortening? And my kind of counterpoint to that is people do it. People make short forms of this even 9-question questionnaire. And this methodology that I'm going to talk about can be used on much longer instruments as well. So there's 2 that get commonly used. The first is the PHQ-2, and it just consists of the first 2 questions that measure having little interest or pleasure and feeling down, depressed, or hopeless. The PHQ-2 was developed based on expert analysis. So a bunch of experts sat in a room and said, let's just ask these 2 questions. I think it'll be good enough. The other shortened form that gets used a lot is the PHQ-8, which is the 9 questions, removing the question on suicidal ideation. The reason why this gets done often, and it was developed with no justification, I believe, is, well, the justification was that questions on suicidal ideation give you really bad data for a lot of social desirability bias reasons, and just in general, they can be kind of problematic to ask. So many people will say, let's just ask 8 items. Post hoc psychometric properties have been shown, like the 8 items work just about as well as the 9 items. And there are actually a lot more shortened forms. They just aren't as commonly used, so I won't mention them by name. But I've seen like a 4 item, a 5 item. If you Google shortened form of the patient health questionnaire, you'll get a variety of papers that use different subsets of items. And this is problematic because it means that you can't really compare things. If someone's only asking 3 questions, someone else is asking 5 questions, it's unclear which shortened form we should use. So these shortened forms were created in ways that are not necessarily reproducible. And a big problem that happens is that these studies are often underpowered. So measurement models have a lot of parameters that need to be estimated. There's just a lot of stuff going on. And sometimes when you only get 300 people in your study, there's a lot of variability in the estimates that you get that you then use for really big decisions. So the question I want to pose is, if you're going to shorten the PHQ-9, how are you going to do it? Should you use 2 items, 8 items, 4 items, 5 items? Which items? How are we going to create a shortened form? So here's how my 6-slide introduction to item response theory. Each of us have some underlying level of depressive symptomatology. Some of us are higher on this, some of us are lower on this. And we're going to say this is a true underlying value that we don't know and can't be measured directly. If you could measure this directly, stop asking questionnaires, just measure it. And I represent this because we don't know it, by this circle and this parameter theta. So each of us have one. were somewhere along the spectrum of depressive symptomatology. So what do? We assume that your underlying level of depression causes or leads to your results on the questions that we ask. So this first rectangle might be, do you feel sad? And you say 1, 2, 3, or 4, like none of the time, rarely, some of the time, always. The next question might be, do you feel hopeless? And it's the same thing. And here I've depicted 3 items for the sake of succinctness on the slide. But in the scale I'm talking about, there would be 9 rectangles. And the assumption here is that I can summarize the data that I get to make inference about the latent trait that I'm really interested in. My goal here is to measure this underlying idea rather than a single symptom score. But not all questions are made equal. Sometimes it's a little bit easier to say, yeah, some of the times, or rarely versus none of the times. Like, it doesn't take that much depression to say, I feel sad. Lots of people feel sad. But maybe the question on suicidal ideation takes a higher level of depression to say, okay, now I have this symptom versus not having it. And that's what I've depicted with these red lines here. So you can imagine going from left to right across the rectangle is like moving up in the level of this underlying trait of depression. So maybe in this bottom question, for the first part of that spectrum, you're most likely to say none of the time. And then you cross a threshold into when it becomes most likely that you would say rarely. And then you cross a threshold into when it's most likely that you would say sometimes, and then always. And these thresholds don't have to be the same across items. They can be at different points of the spectrum. And of course, you could be all the way up in the upper levels of depression and still say never. It's not deterministic. So there is some probability of answering at each category, but it's about what's most likely to be your answer. So first slide with some math on it. This talk is not super technical, but I wanted to show some formulas for the sake of looking like a PhD level statistician. So these thresholds that I was talking about are known as the threshold or difficulty parameters. And I denote them with these betas. So for the first item, the threshold between category 1 and 2 is beta 1, 1. Between 2 and 3 is beta 1, 2. Between 3 and 4 is beta 1, 3. So I have these collection of threshold points. There's another way in which items differ from each other, and that's how good are they at measuring the thing you're trying to measure. So spoiler, if you can only ask one question about depression, you should ask, do you feel depressed? It always pops up as the one with the thickest arrow, the highest discrimination, the one that gives you the most information about the thing you're trying to measure. But we often want more than one item because it gives us a more well-rounded picture of what's going on than just asking a single piece of information. And you can imagine maybe there is a question that is a little bit less related. So we don't want to weight it the same as a question that is very related. And how people often score these scales is they just say, well, you said 1 to question 1, and then a 3, and then a 2, and then a 5, or so on, and they add them all up. But what this fails to account for is that some questions might want more weight than other questions in the scoring process. So item response theory is a way that we get estimates of this underlying trait using observed data on items, accounting for the fact that items have different properties. And when I said earlier that one of the kind of historical methods that people use to assess or to create shortened forms is to cut out things that have low loadings, What I mean is that they take the questions that have really thin arrows and just cut them out. But what does it mean to be not super good, right? That's a judgment call to say, well, I feel like this item wasn't quite good enough, I'm going to get rid of it. It's very rarely written down ahead of time what that procedure is going to look like. So just to put a little bit of notation in case you want to follow along with that, this model is known as the Generalized Partial Credit Model. And there are a few competing models that don't give particularly different results. So this is the one that I tend to use. And it fits conditional on where you are on the latent trait, the probability of scoring at each potential value, so 0, 1, 2, or 3, for that item. And it's a function of your latent trait value, how much true depression you have, which is assumed to be unidimensional and normally distributed. It's a function of those thresholds, those red lines that separate the categories. And it's a function of your discrimination parameter, which is the thickness of those arrows. What is the strength of the association between the item score and the thing you're trying to measure? So due to what is called local independence, but is really just a conditional independence assumption, we assume that the only relationship between how you're measuring different items, how you're answering different items, comes from your value of the latent trait. So given a certain level of depression, the way that you answer question 1 and 2 are independent of each other. So that's conditional independence. And I do just want to point out there's like a individual subscript I that gets dropped from the notation all the time. And it's really just for convenience. But each person has their own value of theta. Each person has their own item responses. So one way that I like to visualize what an item response theory model is doing is from the item category characteristic curve. So what this says, the x-axis here is that standard normal theta that I'm trying to measure. So here you're at like the mean level of depression symptoms. Here are your two standard deviations below the mean. Here are your 4 standard deviations above the mean. And if you look up on the y-axis, it says, what is the most likely category for you to answer? So when you have almost no level of depression, you're most likely to say the lowest category. As you move up in depressive symptomology, now at some point, you're more likely to say a 2 instead of a 1, and then a 3 instead of a 2, or a 4 instead of a 3. And in fact, where these curves intersect, the 1 and the 2, is that threshold parameter. It's that point at which it's most likely to answer the next category. How peaked these curves are relates to how discriminative an item is. So this is the model for just one single item, like question 1. So technical slide 1 of 2 for this part, but I'll show it to you in a picture soon, is that based on Fisher's information, we often will talk about an item information function. So if you're an A3SR student and you've taken my inference course, you might remember our Fisher's information function, the expectation of the negative second derivative of the log likelihood, which comes out to be some function of how discriminative an item is, conditional on your value of the latent trait. And because of that local independence assumption, the amount of information in the whole scale is just the sum of the individual items. And these information functions depend both on the discrimination, the thickness of those arrows, and that really gives us the magnitude of information that we're getting from that specific item. And the threshold places it on the x-axis of latent trait scale. So looking at it as a picture, here in the colored lines or curves is that probability of response for each level of theta. And in the dashed line is the item information function. So we can see at this point at 2, where there's 3 categories that are kind of close to each other, that's where we get the most discriminative ability between different values of the latent trait, where we really hone in on what we're trying to estimate. So why am I showing you all of this? Well, if the height of an item information function is dependent on how the thickness of the arrow, and I've told you that some way that people shorten forms is by saying, well, if an item doesn't really relate to what I'm trying to measure, let's get rid of it. Well, that's going to seem like, let's get rid of the items that have these low information functions. But there's another factor here, which is where they're located on the scale. And that gets ignored when we don't look at the item as a whole. So here on the left, I have the item information functions for all 9 questions of the PHQ-9 based on the data that I'm about to talk to you about. And the sum point-wise across the x-axis about the information in the whole scale. So the first question one might ask is, well, here I see an information of 20. Is that a lot? Well, we don't really know. I mean, maybe you do know, but it's not a great like interpretable measure. And if I take away items, because this curve on the right is the sum of the curves on the left, if I'm adding fewer items, the test information is going to decrease. Like this curve is going to get lower on the right, which means I'm going to have less information to measure the thing I'm trying to measure, that underlying value of depression symptoms. So I can't just say, let me get rid of items until my test information is at like a reasonable level, because it's unclear what a reasonable level is. So fundamentally, we have an item selection problem. I started with 9, I want to choose some. But I want to keep this about the goal of the process. My goal is not to measure the items, my goal is to measure the latent trait. So I want to create a shortened form. Let's do brute force. I have a pretty good computer. So what if I take all possible forms to consider? So say I started with 18 items. There's 2 to the 18th, or 262,144 possible shortened forms that you might look at. Well, my computer can handle generating that given a few minutes, I guess. But that's going to be a lot of things to decide between, a lot of options that we're going to have to make a decision to select just one shortened form. So I'd like to come up with a systematic way to think about this problem. So my procedure has 3 steps. I'm going to take a data set. I'm going to fit that IRT model, the one that I just showed you with the curves. I'm going to run what's known as optimal test assembly and apply decision rules. So 3 steps to the process to go through. Now, I am probably the most fortunate statistician in the world when it comes to having the world's best collaborators. And I collaborate with this group based in Montreal known as the Depressed Project, the Depression Screening Data. And what they do is they literally call up people who have applied the PHQ-9 and other measures and have gold star ratings, like a psychiatrist or a structured interview rating of depression. And they say, will you send me your de-identified individual patient level or participant level data in exchange for some form of co-authorship usually? And magically, like, they come up with data sets of like 35,000, 70,000 individuals that are clustered into these, primary studies. And it's really amazing. It takes a lot of work to create, but they end up with, before I was complaining about underpowered studies, they can come up with like thousands of people that you can include for any one individual analysis you're trying to do, if you can work with them. So my first part of the project, which I did back in like 2018, used almost 8,000 participants. There's about a 10% prevalence of major depression from 20 primary studies conducted in English. And if I have a chance to talk about kind of the external validation piece, then there was a second external validation data set, just because it was collected later on in time, of about 35,000 more participants from 75 studies. And especially for the people, for the students in the call, I want to take a second to talk about how hard it is to collect data. Because I think like when I started being a statistician, I would often say, okay, I got my spreadsheet, it has a lot of ones and zeros and numbers in it, ready, set, go. But to get these like 7,800 participants, my collaborators looked through over 5,000 abstracts, excluded ones that didn't have the right measures, ended up with 200 papers that they had to read and look at the eligibility criteria, and then look at which ones were unique studies, which ones had primary data, which ones were, and then include ones that were unpublished, like calling authors that maybe that they could come up with, but didn't have their papers published yet, and then get consent from all of these authors for the data to end up with 58 data sets with primary data. And then we excluded ones that were not conducted in English because of potential problems comparing measurement across languages. And I excluded ones that used a certain type of semi-structured interview to classify major depression, like in my gold star ratings. And that's because it's kind of known to not do a great job. And that's how I ended up with 20 studies. But the work to get this data set is like, it takes like a whole team of people years to do. So I tell you this just in a goal of, I guess, creating some appreciation for data sets that maybe were handed and get to work with, that it really does take a lot of work to get there. So I told you my process has 3 steps. Step 1 was fit that item response theory model. And here for the first time, I'm showing you the 9 questions on the patient health questionnaire. So the text of the question is here, and the discrimination parameter is on the right. And the discrimination parameters, remember, is that thickness of the arrow. How much does this question relate to the thing I'm trying to measure? And I told you, spoiler alert, if you could only ask one question, the highest discrimination is on the one that just like asks if you're depressed. And the lowest discrimination is the question about falling or staying asleep. Not that it isn't an interesting symptom to talk about, but maybe it's being caused by other things, like other problems that you have that aren't depression. And when people will just kind of select based on discrimination parameters, they'd say, oh, well, 0.93, that's the lowest, let's cut that item. And then 1.08, okay, the appetite or overeating, that's still a small number, let's cut that item. But they don't tell me what a big value or small value is for this discrimination parameter. So 3 steps: fit the model, run optimal test assembly, apply decision rules. So what is optimal test assembly? Optimal test assembly is an algorithmic process that maximizes a function subject to a set of constraints. It is a way of, it's just like a maximization procedure. So usually when you have a function you want to maximize, you hope that you can take its derivative, set it equal to 0, and be like, I found the maximum. But when it's a constrained optimization problem, it gets into a little bit more complicated applied math. And some applied mathematicians who, really work on numerical problems have come up with this process. And what I'm going to do is I'm going to use optimal test assembly to come up with 9 candidates. First is the best one item. If you could only ask one item, which item would it be? Then is the best 2 item. Which 2 items would you ask if you could only ask 2 items? The best 3 items, and so on, up to the full-length form. And when I say best, I mean maximizes the amount of information across the range of the latent trait. So if you think back to those information curves I showed you, the ones that are kind of giving me the most information across the whole spectrum. So technical details, 1 of 3. Suppose that you're trying to make a shortened form, say of length 5, k equals 5. So what I'm going to do is define a set of constraints through the creation of binary indicators, 0 or 1. So 1 would mean I include that item, 0 would mean I don't. So the function that I'm trying to maximize is the sum over all my items from 1 to 9 of the information function times the indicator of whether it's being included. So because kj is an indicator, it only counts up the ones that are getting included in the form. And the goal here is to figure out, well, which ones are getting included in the form. And we're going to do this through what's known as a branch and bound modified simplex method. So if the goal of optimal test assembly is to maximize the test information of the generated form, then what I'm trying to do is to maximize this linear objective function, it was just a sum, representing the total amount of information in a shortened form subject to the constraints of the length of the form I'm creating, like the best 5 items, say, and the fact that a question is either in or out. Those k's cannot be like a half. I can't ask half of a question. And it does so through this branch and bound method, which is a way to search the space of all possible outcomes, of all possible shortened forms. And the technical details for this are really explicitly laid out in a paper I wrote in 2018 in Statistical Methods for Medical Research, which I'm happy to share with anyone who's interested. So what it does is it starts with this first random guess at which 5 items you should consider. And then for each item, it branches and says, what if I did include it? What if I didn't include it? And it compares based on the total amount of information, each of those possible next choices. And it continues to branch out from there until either you get to a solution that's infeasible, like it's of the wrong length, or a solution that's worse than the one you're currently considering. And based on some math, we know that adding more constraints can only constrain our problem more. So if we find an infeasible solution, it doesn't help to keep going and it gets bounded. So branching and then bounding when we find places in the space that aren't helpful to us. So what does this leave me with? So here, I actually ran for the PHQ creation of 16 candidate forms. So I said we were going to find the best 1 item, the best 2 items, and so on. And if you look across the rows here in the top part of the table, that is like, so if you could only ask 3 items and you consider all 9 as your start point, you would ask questions 1, 2, and 9. But because the PHQ 8 is so commonly used and people really have problems with this item 9, we a priori made the decision to look at 8 other potential shortened forms, which was starting with the PHQ 8 as our long form and shortening from there. So that's why I have 16 options. So if I look at the best 4 items when I never considered item 9, it would be the little interest question, the feeling down question, the feeling of failure question, and the question about physical movement. So I started out with a full-length form. I talked to you about 2 shortened forms. And now you're like, thanks, Daphna. I have to consider 16 forms? This problem seems to be going backwards, right? This is not going in the right direction. So, well, it will be. But I can see potentially why someone would look at this and say, I've made it more complicated. Well, what I have here is I have 16 candidates. So like, I don't know, a good Democratic primary. of shortened forms that represent the best set of items that maximize the amount of information. So what I'm going to do is I'm going to apply step 3 of my process and select which of these 16 gives me the shortest possible form while maintaining desirable psychometric properties. So fit a model, get my candidates, apply decision rules. We're at step 3. So once I generate this set of candidate forms, I need to choose which candidate maintains the desirable properties, but by taking the shortest possible form that does so. And I can't do this based on test information because there's no obvious threshold that at which one would conclude that a shortened form has adequate test information. So what I'm going to do is I'm going to take measurement properties that we often care about, things that we look at when we say, oh, this scale is reliable and valid. So I'm going to look at reliability, concurrent validity, and diagnostic accuracy. So there's going to be 5 rules, and we're going to want to pass all 5 standards. So the first is that I'm going to look at a measure of reliability known as Cronbach's alpha and say a form is only acceptable if it has an alpha of at least 0.8. Now, those of you familiar with reliability might say Cronbach's alpha is like not the best measure. The reason why I use it is that in the published literature that uses these scales, this is what people look at. And I wanted my shortened form to have face validity. I wanted the people who are used to using these forms to have it have properties that they recognize as being good. And I will talk about later about sensitivity to these rules and work I'm doing currently. But for now, we're just going to look at Cronbach's alpha. The second thing is that I'm going to measure concurrent validity. So I want the correlation between scores on a shortened form and on the full length form to be high, right? I want them to be pretty related to each other. And I'm going to do this in 2 ways. First, I'm going to use the factor scores, the estimates of that latent trait that I get from my complicated model. And I'm going to keep that correlation to be at least 0.9. I'm also going to do this with summed scores, where you just take your answers to all 9 questions or all questions on the shortened form and add them up. Why do this in 2 ways? Well, factor scores are known to be better, and summed scores are known to be used in practice. So let's hold ourselves to both standards and make sure we're doing well on both of them. And you might say, well, where did 0.8, 0.9, and 0.9 come from? They were what I call investigator defined, otherwise known as I chose them. And that is definitely a point that, I'm thinking about a lot these days, but at least I wrote them down ahead of time and you could apply the same rules or you could change the rules. So unlike when people select based on discrimination parameters, I gave a rule that is reproducible. The next thing that I want to look at is known as diagnostic accuracy. So the data set that I'm using has a gold standard. It has either a fully or semi-structured interview on each participant. And so I know whether they were rated as having depression or not. And I'm going to look at sensitivity and specificity. Sensitivity and specificity are things maybe you're now, more aware of given like COVID tests and things like that. But basically sensitivity is the proportion of those who have the condition that received a positive result on the test. So the probability of a high score on my form for the people who actually were rated to have depression. And specificity is the true negative rate, the probability of having a low score for those people who don't have depression. And you want both of these numbers to be high, right? You want to make sure that you're correctly classifying people with your measure. And I use something known as Uden's J, which is how people will often look at a cutoff for a scale, which is sensitivity plus specificity minus 1. But I tend to also present sensitivity and specificity for all possible cutoffs when I'm looking at a scale, because Uden's J is a little bit disputed in the literature these days. So sensitivity and specificity with kind of regular data is not too hard to calculate. You make your contingency table, you remember your probability rules and what your denominator is going to be. But my data structure is a little bit more complicated. So remember that I've gotten data from primary studies, like different PIs who collected data, and I'm pooling that data for what's known as an individual participant data meta-analysis. And different studies might be different from each other. There's heterogeneity between studies. So my good friend and collaborator, Dr. Brooke Levis, used bivariate random effects models to simultaneously estimate sensitivity and specificity while accounting for the correlation between them, as well as the precision of estimates within studies. The mathematical details of this are presented in a paper that I just published in a journal called Methods at the end of last year, which I'm also happy to share. But what these models do is they give me an estimate of sensitivity and specificity while accounting for the structure of the data. And this is a good lesson in when a problem seems hard, you can find a solution for it. It just might be a little tricky. So don't give up on it. Now, I want the sensitivity and specificity for the short form and the full length form to be the same. I don't want to lose sensitivity and specificity. So then you might say, well, let's run a hypothesis test. Null hypothesis is that they're the same, right? The difference between them is 0. Alternative hypothesis is that they're different. Where's the problem in that? Well, the problem is that we can't accept the null hypothesis in a hypothesis test, but my goal is that null hypothesis. And this is where equivalence testing comes in. So again, if you take my inference course for the A3SR students on the call, I just taught you this on Monday. So equivalence testing comes from clinical trials and basically swaps the null and alternative hypotheses and says, if the difference between these two values of sensitivity is too large, larger than some like tolerance of what I would care about, that's the null. And if it's small enough, that's the alternative. So when I reject the null in favor of the alternative, I'm actually going to get equivalence, which is my goal. So what I'm going to do is create 2 more rules. The first is that the difference in sensitivities is going to be considered, or these sensitivities are going to be considered equivalent within a tolerance of some small number, like I think I used 0.05 for the full length and short form, and the same thing for specificity. Now, we know you only need 4 things to run a hypothesis test. You need hypotheses, you need an alpha, you need a sampling distribution, and you need a test statistic. There's no analytical answer for the sampling distribution for equivalence tests of diagnostic accuracy measures. So I can't just like p-norm or t-table it to get my p-values. But I didn't want to be stuck, so I used the bootstrap. And what I did is controlling for the number of people who had depression and not having depression in each iteration, I resample my original data set with replacement to generate new artificial data sets and calculate sensitivity and specificity to come up with sampling distributions. I did 2,000 iterations, and for each, I calculated sensitivity and specificity for all 16 of my candidates. And I used these sampling distributions to conduct a one-sided equivalence test to check that my new sensitivity and specificity weren't inferior to the old ones. Now, these 5 decision rules represent different desirable properties. So I need to pass all 5 of these. And yes, they're investigator defined, but I wrote them down ahead of time. And I did a giant simulation study in a paper in Statistical Methods for Medical Research, which showed that they're actually quite replicable. So simulating different data sets, I got reasonably the same solutions across a bunch of iterations. So I'm relatively happy with them. So I did it. I chose out of my 16 candidates the shortened form that had items 1, 2, 6, and 8 was the shortest possible form that passed all 5 decision rules. So it had a Cronbach's alpha of 0.8 versus 0.866 on the full form. It had those correlations above 0.9, and the sensitivity and specificity were at a cutoff of 4, were considered equivalent, or at least non-inferior. And this is the form. So the first question is little interest or pleasure in doing things, feeling down, depressed, or hopeless, feeling bad about yourself, or moving or speaking so slowly that other people could have noticed, or the opposite, being fidgety. So I was very pleased once I saw this and talked to my collaborators that the first 2 questions that came up based on my reproducible statistical method are actually the 2 core depression items that make up the PHQ-2. You need one of these 2 things in order to get a depression diagnosis. It is not possible to get one without either depressed mood or loss of interest. The other 2 were an affective or cognitive item and a somatic item. So qualitatively, my PHQ-DEP4 represented depressive symptomology pretty well. And that's not rigged, it just kind of happened to come out in the data. And I actually explicitly considered the PHQ-8, which I did on purpose, and the PHQ-2. That just popped up based on optimal test assembly. And neither were selected. This 4 one here was the one that was selected. So what does that tell me? Well, my 4-item questionnaire has lower sensitivity than the PHQ-2, but higher specificity. And maybe it's like this middle ground between shortening the full-length scale too much, but also retaining good desirable measurement and diagnostic properties. And it may be a useful option in some contexts because it's shorter than the 8 and 9, but has a wider score distribution than the 2. So I know I'm running out of time, so fairly quickly, I just in like the last few months ran an external validation study where I took 35,000 new participants across 75 studies. I did not externally validate the selection of the PHQ-DEP4, but rather does a cutoff of 4 on it continue to perform equivalently in diagnostic accuracy to the PHQ-9's well-loved cutoff of 10. I ran the same type of mixed effects models to get my estimates of the sensitivity and specificity. I got my sampling distributions, and I ended up finding that sensitivity was fine, or actually a bit better, but specificity dropped a bit. And here's like a very sad thing to say. Chances are the fact that I didn't find equivalence in my external validation study is a sample size problem. And no one wants to hear that 35,000 participants might not be enough. But it was very hard to do a sample size calculation for this. Like, 3 of us really racked our brains about it for quite a while. And we ended up saying, well, we have all the data we can possibly get. This is like every study that's applied this measure in the last 10 years. So we're going to have to go with it. But yeah, sometimes 35,000 participants might not even be a powered study, which is pretty sad. No collaborator wants to hear that. Okay, so to end up, is this reasonable? Well, all the data that's needed to run my process is usually collected in the validation of an original scale. So why not throw it in as the last step? I've done this 5 times so far, and it's been adopted by a few others to shorten some forms. There's a group of researchers in China that have been using this method to shorten their forms. And when should you shorten a form? And maybe I should have pitched this at the very beginning, but shortened forms are good when you're looking at like summed or factor scores, just composite measures of all the items, maybe in a screening study or an outcome or predictor in a model. Now, if you need item level answers for everything, like maybe for direct patient care, you might want to ask all the items. That's a benefit analysis that you have to do. Like if one of the omitted items is an important attribute of your population, then maybe you want all the item scores. So what am I working on now? I have an A3SR student who's currently working on getting my code into an R package. I would like to externally validate the selection procedure, not just the cutoff. I'm hoping to look at the impact of setting different decision rules and how that changes things. And then maybe some cross-validation for overfitting or some Bayesian approaches for smaller sample sizes and to incorporate expert opinions within priors. So I really want to thank my two students, Alex, and then an A3SR alum, Miyabi Ishihara, when she was a student of ours, actually did the bulk of this PHQ analysis. She's currently a PhD candidate at UC Berkeley in statistics. The DEPRESS team, who is run by these three wonderful collaborators, and of course, everyone who collected the actual data, and most importantly, the participants. You know, I appreciate their time for answering scales and being a part of scientific studies. So I'm happy to take any questions in the 6 minutes left. If you'd like to read any of these papers, I'm happy to share them. Here's my email address.
All right, so on behalf of everybody, first, let's thank Daphna for a wonderful talk. And yeah, questions, just feel free to unmute yourself or ask them in the chat if you prefer. And as always, I'd like to particularly encourage any students on this call to ask Daphna questions.
I would also like to encourage students on the call, since you mostly know me and I'm not that scary. Also, non-students are fine too. Or not. Maybe I was
I have questions, so I could always like take up time, but okay, I'll ask one real quick that just occurred to me, I think from the beginning of your talk, which is, I was wondering if you know how these kinds of different versions of questionnaires end up in practice, you know, so say you as a researcher, you discover that the PHQ-4 has all these nice properties, and there are many circumstances in which it would be perhaps better to use it than PHQ-9 or the PHQ-2. So how does it get to the point where clinicians are using the PHQ-4? Is it like your collaborators use it and then they hope that clinicians like read their papers, or is there some sort of more formalized way that everybody someday will be using, say, the PHQ-4?
So the short answer is it's really hard, but also because I have buy-in from all of these people who actually collect data, who gave me their data, I can also email them and say, look at what I found. And I can pitch my measure to them. But a lot of getting your work out there and actually used in practice is doing it yourself. Starting to use this in my own projects, as well as giving talks, getting the word out there, and trying to get the word out there, not just within the statistical community, but at large. And this is where being able to talk about statistics really is important, because the type of people who are collecting this data, they don't care what optimal test assembly is. They just want to see why this scale is as good or potentially better than something else. And yeah, I think that's really a challenge, and something that we all have to work on, is getting that information out there about the work that we do that's more technical.
There's a question in the chat, and Pat has his hand raised. I think Roberts was there first, and maybe we go to Robert first. So I'll read it out. Mm-hmm. If we assume that different measures have different social desirability biases, maybe item 9 better discriminates those willing to answer the question rather than theta for depression, do we need to adjust our approach?
So the biggest competitor to shortening a form for a pen and paper fixed form is computerized adaptive testing, which literally just asks different questions to people based on their answers to previous questions. This is how like the GREs are administered these days, or at least when I took them a million years ago. So in that case, like if you want to create a computerized adaptive test, every clinical practice has like an iPad or computer to do this. There are ways to come up with individualized shortened forms, but I find often people want to be asking the same exact questions to everyone in their study for comparability reasons, in which case you don't want to have to include or not include an item based on whether it's going to do well with a specific person.
And it looks like we probably have time for maybe one more question. And
As his hand raised. Yeah.
Okay, very nice talk. I'm actually at a park in in the Upper West Side waiting for another meeting, but I really enjoyed your talk. It was so clear, and your program of research is wonderful. So let me just ask you a possible extension question. Suppose that someone came to you and said, you know, I'm in the military and I want to do a screening to find people who are have major depression. So they're not interested in specificity as much as sensitivity because they have the resources to do the follow-up. They simply want to eliminate the people for follow-up. It seems to me that all you would do is go back to your second step and change your optimization function instead of having information across the whole range, maybe to emphasize the information at the top end. Have you done anything like this, and would that be a reasonable alternative direction?
I think that's a very reasonable alternative direction. And you're right that I could maximize information across only a part of the range. I can also, instead of using Uden's J, which gave me a cutoff of 4, I now present sensitivity and specificity for every possible cutoff, which would allow any specific user to choose a different cutoff of the scale. So yes, there's 2 places we need to look at this: which items we're asking and what cutoff we're using to check up for follow-ups. So there are places where people will prioritize sensitivity and places where people will prioritize specificity.
Thank you so much.
Thanks.
All right, so in the interest of time, I think we'll end it here. So I will thank Daphna again on behalf of everybody for that wonderful and super clear talk. And, you know, for those of you who have more questions, follow up over email or in person. And thanks, and we'll see you at our next PRISM seminar, which is in maybe a month's time. I forget exactly, but it's on our schedule. All right, bye everybody. Have a great day.
Everyone.